All right, everybody, welcome back to Top Comics Pressing. This is going to be the first in a series of videos trying to just help us understand some basic bits of science and how they apply to comic books, particularly cleaning and pressing them. And so in this video, what we're going to do is try to answer the basic question about how acidic are our comic books, and we're going to try to couple that to how worried we need to be about exposing them to things like hydrogen peroxide. And so to try to answer this question, what we're going to do is use an instrument, and my simplest instrument is just going to be these pH strips. I happen to buy these off of Amazon, but you can get pH strips in a lot of different places. This is just the brand that popped up as an Amazon recommendation when I searched. And I like them because you can tell the pH based on 4 different colors. And so we can go ahead and compare our test strip to these colors to figure out what pH we're dealing with. So let's just double check that and try to calibrate our instrument here with the pH strip. So the first thing I have is some distilled vinegar. This is just what I bought at the store. 5% acidity. We had it in our kitchen right off the bat. And so hopefully if it says 5% acidity, it'll be acidic. And so I should probably tell my wife I'm dunking the strip right in the bottle, but oh well, there we go. So in this particular case, that was our vinegar. We can go ahead and line up those results with our strip here. And definitely that top square to me looks too yellow to be a 3. It looks like it lines up pretty well with the 2, and it's nowhere near pink enough to be a number 1. And so again, that lines up pretty well with the 2. And so we're going to go ahead and call that pH 2 there, I think, for the vinegar. Cool. Next up here, we want to check out something on the basic side of the pH spectrum. And so let's just go ahead and grab some Windex, which should hopefully be on that side. You might be worried about the blue tinge in the Windex, but it's pretty dilute blue, and I think we'll see that it affects the pH strip quite dramatically and pretty instantly. So there you go. So definitely that really kind of pinkish square turned, and we got a pretty good change in the top blue and purple square as well. And let's just check and see if that lines up with anything here. And I think if we slide that along there, it looks like it lines up pretty well with pH 11. So it looks good. The third one down doesn't quite look as burgundy as 12. And so we're going to call that pH 11 as a line up there. So let's just go ahead and put that there. That's our Windex at pH 11. Next on up then, let's just check some water. And it turns out if you do a quick Google search for how acidic water is, you should see that it should, in principle, be a perfectly centered number 7, should have pH 7. We're going to find out that this is probably not going to be 7 when we dunk it in our distilled water here. And there's a very good reason for that. And so before you freak out on me, just sit tight. I'll get there in a second. And if I scroll this along there, you know, I might be able to line that up pretty good with the 6. To me, that second one down does not look green enough to be a 7, and the top square does not look purple enough, but it does look like it lines up pretty darn well with that 6. And so I'm going to call our distilled water, or DI water, is going to be a 6, at least the stuff that we've got here. And go ahead, if you don't believe me, buy some pH strips and check your own bottle of distilled water. I bet you it comes in at exactly 6 as well. And there's a reason for that, and I'll get there again. So let's check our hydrogen peroxide. Now, some people might correctly identify that hydrogen peroxide is a weak acid, but it's not going to be a very good acid. It is actually going to be a pathetically weak acid. Even weaker than Peter Parker's most feeble foe, and I'll explain that and how to interpret that a little bit later. You'll notice that this is the Up and Up brand, so I think this is from Target's household brand, and we can check that versus our strip here, and lo and behold, that comes in again pretty close to pH 6. That top square is a little too gray to be a 5, and so I think that lines up, and the second one is more green than yellow, so I think that's going to be a 6. And you know, even if we're not worried about exactly what the number is, the important thing is if we map these two right next to each other, you can see they line up pretty much identical. So the hydrogen peroxide and that distilled water are going to be nearly identical at pH 6. And just so you don't think I'm screwing with you, we can put the Target brand aside and look at the Meyer brand that I've got here. I use both of these for working with comic books. I don't really care what store brand I buy. And so we'll just dunk this one in this bottle. See what that one comes out looking like. And again, it's going to be right at 6, and that'll match up pretty well there. So you might ask, well, what else could we look at? Well, maybe we got a wedge of orange here. Most people identify citrus as being acidic, and so let's just grab a strip here, kind of juice out our citrus fruit, rub that across there, and see what we come up with. Indeed, that looks like it's a little bit more acidic, and if I look at it, this is going to be a quite sharp piece of fruit there. I would say that that's closer to a 3 than a 4. You know, maybe it's not all the way to a 3, maybe it's a 3.3 or 3.5 or something like that. But we'll go ahead and assign it a 3 for simplicity, and just leave that right there. And now we have to answer the question, how acidic is our comic book? And to address this, I have here a coverless copy of Lois Lane number 116, and I've squirted it with some water to try to extract whatever I can off that page. And we're just going to go ahead and take our test strip and just stick it on in there and give it a good push to try to soak up some of whatever goodies are hanging out. Let's see how we did there. Might need a few more drops of water in there to really help us get out some of the goodies. This is just my water squirter. All right, it's coming out looking acidic. I'm gonna say that that's a 5. Definitely the top one I think is more bright than a 6, and maybe on the edges it's closer to a 4. Let's look at the second square down. I think it's not quite that yellow. We'll call it a 4.5. I don't think it quite matches the 5. It's not quite to a 4. It's not quite a 5. It's not quite a 4. We'll call that one a 4.5. So that is our Lois Lane copy. The next one up here I have is a pretty epically trashed copy of Amazing Spider-Man 307. You'll notice it has pretty extensive stains on the back, and it's got all kinds of staple damage detached on the bottom. This thing has seen better days for sure. And let's just go ahead and extract top of this stuff too and see what it comes about at. Yeah, that looks like a pretty good match for the Lois Lane. Again, I think it's going to be, you know, the second one down, it's going to be a 4. We'll call that a 4. Maybe 4.5. Yeah, 4.5. We're going to call both comics 4.5 today. That looks pretty good. I'm going to move those over here so that they don't make more of a mess. You can see that they're leaving kind of some yellow grossness on my desk. Okay, so I think this answers some basic questions about, you know, just what we're measuring here, and we can draw a couple of important conclusions. One of which is that vinegar and my citrus fruit are definitely more acidic than what I'm extracting off a comic book. The comic books are indeed slightly more acidic than either distilled water or the hydrogen peroxide, and that Windex is definitely basic there to help us, you know, kind of demonstrate that indeed we can at least measure base and give us confidence that these aren't erroneous. You'll notice that these will continue to kind of bleed out and discolor as we go through the rest of this. So I encourage you to essentially ignore that. So let's just dive into some acid-base theory here. So any acid which is reflected as HA can dissociate into a proton, H+, plus A-, we'll just call her conjugate base. And this equilibrium we give a special value to, which is Ka, and that basically tells you how much stuff is over here and how much stuff stays over here. And so the Ka equals the concentration of H+ when at equilibrium times the concentration of A- all over the value HA. And for those of you that went through AP chemistry or college chemistry, you did what were called ice tables to figure out the pH that a acid would reach equilibrium at. So if you're curious for some advanced problem solving, search that. There's tons of help available. Now, the water can also do this all on its own. So water can dissociate to generate H+ and OH-. This gets a special value, Kw, and Kw happens to equal 10 to the negative 14. And that also happens to then equal the concentration of H+ over OH minus. And technically this is over water, but it turns out we drop liquids from the equilibrium, and so it's really just H plus times the concentration of OH minus. Now these values on their own are pretty crazy, and so to simplify life, we take the P value, or the pKa, and that is equal to the negative log of the of Ka. And it turns out that's going to be a lot more useful value. And we're really going to be interested in comparing pKa to pH. So the pH is going to be equal to the negative log of the H plus concentration. Now what's important about this is the log scale is a 10x scale. And so that means 1 unit is tenfold. So if we go from a pKa of 5 to a pKa of 4, that acid is 10 times stronger. And if we go from a a pH of 7 to a pH of, say, 6, that means that this is 10 times more acidic. And don't worry, haven't forgotten about that. We'll get back to why that water is not exactly 7, which is what it should be based on the Kw. So you get to there by adding up the concentration of this, which should be 10 to the negative 7, and you do the same thing for the hydroxide, which is 10 to the negative 7, and you multiply those together and you get the 14, and the pKw equals 14. And so that's where you get the exactly perfect pH 7 for perfectly pure water, is it's 10 times 10 to the negative 7 for hydronium, and that then equals pH 7. So pure water equals pH 7. Now again, before you get freaking out on me and start going to throw away all your distilled water because it's not pure enough, we'll explain that one here in a minute. Okay, where was I going with this? So we've got a bunch of different acids over here, and we want to compare how acidic they are and how worried we are about these. So in general terms, we have strong acids and we have weak acids. And a strong acid is an acid that fully dissociates and goes over here. And so the way that is reflected here is that the Ka is greater than 1, and it favors the dissociated state. A weak acid prefers to hang out on this side, and that means that it prefers to have more Ha than either of these two, and that means the Ka value is quite small. That means that the pKa value, though, is quite large. Okay, and the reason for that is we've got this negative log bit in there, and that effectively inverts it. Makes it a little confusing because strong acids have low pKa's, and and weak acids, the weaker they get, the higher their pKa. I didn't come up with the math. Don't blame me for it. It seems a little backwards. I get it. It's something that I've had to live with for quite some time. The important thing I want to point out, though, for weak acids is it just means that it is disfavored to dissociate. It wants to hang out over here. But it doesn't tell you by how much. And because this is a log scale, delta 1 pKa is 10x. And so we want to compare those pKa's to figure out how strong our acids are. Now, thankfully for us, there are pKa tables. And if we look at a very strong acid like hydrochloric acid, its value is -7. It is a very acidic acid. It has a very low pKa. If we look at H2O2, we can find its pKa here in a second. And if we look at acetic acid, which is what is in our household vinegar there, we can look that up. And then we can look at our citric acid that was in our piece of citrus, correctly named. All right, and so let's just go ahead and find those values. And if you're unfamiliar with how to do so, the first thing I would recommend is actually looking at Wikipedia. And you might laugh at me and say, Joe, Wikipedia is not a very authoritative source in the real world. I was told in college I couldn't cite Wikipedia. Well, it turns out for basic chemical constants, it actually is a great source of information because it auto-populates it from a couple of chemistry databases, and it's pretty hard for somebody to tamper with that. And so, you know, I wouldn't write home on a PhD thesis that I cited this, but for a quick view, we can actually go ahead and find out that the acidity, the pKa here for hydrogen peroxide is 11.75, and that will hold up pretty strict scrutiny from most professional chemists, because it turns out that is going to be exactly what they recall from their active knowledge. Now, let's just Google really fast, what is vinegar? Well, the Wikipedia page on vinegar says it's 5 to 8% acetic acid by volume. Ours is 5%, says so right on the label, and we can go ahead then and look at acetic acid. By the way, this is the chemical structure for acetic acid, and this double bond OOH is going to be the carboxylic acid functional group. And if we scroll down here, again, we can find that the pKa of acetic acid is going to be 4.756, which is very precise because we've measured that pKa so many times. All right, then we can look at citric acid. Citric acid is going to be a lot more complicated acid, and you'll notice it actually has 1, 2, 3 carboxylic acids, and any of those can be deprotonated, which is going to be why we're going to have 3 pKa values here. So we're going to have 3.13, 4.76, and 6.39. And this means that citric acid can actually serve as an acid 3 separate times, once at each of these pKa's. And you might ask me which one's which, but it turns out we don't really know. We just know that it is deprotonated once at those pHs, and every time it gets deprotonated, it builds up more negative charge, and that makes it harder to deprotonate again, and so the pKa values drift up with subsequent deprotonations. Okay, so that's pretty cool, and now we can go ahead and use those pKa's and think about the pH at which they become relevant. And so if we make a little graph here, we can have percent relative acidity of our acid, and at very low pHs, none of these things are going to be acidic, and then eventually they're going to become acidic, and they'll reach 100% deprotonated, or at least 99.999%, if we want to be technical about it. And then this would be our pH scale. It turns out this center point of the inflection is going to be the pKa. And so for something like hydrogen peroxide, that is going to be 11.75 for H2O2. And we can use our math here based on the equilibrium constant Ka coupled with the pKa and the pH, and we can do some quick log math and figure out that, let's say at a pH of 10.75 or at 12.75, that is 1 plus 1 unit or minus 1 unit, we would be at 10% deprotonated, and respectively here we would be at 90%. And it's going to get easier from here, because then if we drift up to 13.75, we would be at 99% deprotonated, and if we drift down to 9.75, then we would be at 1% deprotonated, and if we drift to 8.75, we would be at 0.1% deprotonated. And if we keep going, that means that's 7.75, which is still basic. We are at a pathetic 0.01% deprotonated. If we go to 6.75, 0.001, and at 5.75, which by the way is still more basic than our comic books, we are at 0.0001% deprotonated. And so while something like hydrogen peroxide is a weak acid, it is such a pathetically weak acid that it doesn't even start to function as an acid really until we get all the way up to 9.75 pH. And even there, it's only 1% an acid. And so again, it is a pretty pathetically weak acid. That is very different from acetic acid or from citric acid, which are both much, much stronger acids. Not only are they a little bit stronger, let's just ignore that 6 there and subtract these. So 11.75 minus 4.75, let me see here, 5, 6, 7, 8, 9, 10, 11, so that's 7. So that's 10 to the 7th more acidic. So 1, 2, 3, 4, 5, 6, 7. Need one more in there. So what is that? 10 million? 10 billion? Wait, 1, 2, 3, 4, 5, 6, 7. Yeah, there we go. So 1,000, million. Yeah, so 10 million-ish. So that's pretty acidic by comparison to hydrogen peroxide. They're both, by the way, technically weak acids because both of them prefer to sit over here. Neither of them fully disassociate, but, you know, what's 10 million fold amongst friends? If you're worried about 10 million fold, tell you what, I will trade you my copy of Amazing Spider-Man 307, and you can trade me your copy of Action Comics #1. That's probably about a 10 million fold difference. If there are any takers, please leave it in the messages. I've got a copy right here. All right. Okay, so now there are a couple of things you're very curious about. One of which is I still haven't addressed this. The other of which is at this point you're saying, dude, Joe, citric acid here is 3.13 pKa and acetic acid is 4.75. That means citric acid should be the stronger acid, but when we actually measured it, the citric acid was at 3 and the vinegar was at 2. What gives there? Well, there's two things going on here, one of which is the concentrations. So all this math has to do with how much acid there was originally to start with. And the vinegar being at 5% acidity is actually going to be a fairly concentrated acid. There's no way there's 5% citric acid in my fruit here. There's probably 5% sugar because these things were delicious before, but there's probably not 5% citric acid. It's probably much, much lower than that. The other thing that it could be is buffers. And buffers are kind of chemistry's way of keeping the pH where it should be. So biology, buffers around pH 7 using phosphate. It's really closer to pH 7.2 with phosphate. And doing that, biology can keep the pH very close to that 7.2 in most systems. There are exceptions, but generally speaking, 7.2 is a pretty good pH. As it happens, a buffer is both an acid and a base that functions around its pKa. So if your phosphate and your pKa is 7.2, then you're going to be a really good acid or buffer in that range. And what that basically means is we're going to look at this range when we're dealing with a buffer. And that buffer has a way then of consuming acid and base to make sure that the pKa doesn't shift a whole lot. If you want the math behind it, it is called the Henderson-Hasselbalch equations, and you can Google that on your own. It's much more complicated than the discussion I want to have here. But the basic thing is going to be true for our tangerine wedge or our clementine wedge here. It has two different things that make it experimentally less acidic than our vinegar. Even though our vinegar technically is a weaker acid. Although it's not weaker by that much, right? It's really a little bit more than a pKa unit. That's still tenfold. I'll give you that's still tenfold. But the two different things are going to be it's simply less concentrated acid and it's going to be in a more complex biological buffer. This is simply acetic acid and water. It's distilled. I'm sure it's artificial. There's no way that this is real true vinegar. This is totally manufactured and then diluted with water. And that is a very simple system of just acetic acid and water. Okay, cool. So here we've got a whole bunch of stuff. What I still haven't done is addressed this DI water. So DI water question. What was up with that? Well, it turns out we have a pesky molecule in the air called carbon dioxide. And carbon dioxide, as it happens, can go ahead and react with water to make carbonic acid. It's going to be in equilibrium, but it makes H2CO3. And carbonic acid, by the way, is the same fizzy you get in your soda. So if you don't believe me on this one, get some pH strips, sit there with a soda stream till you've got more bubbles coming out of it, and measure that a whole bunch. And you'll see that that is pretty much the case. Now, unfortunately, due to global warming, the concentration of CO2 has been going up in the air, and that causes some issues in the environment, as you might know. So shellfish have a harder time maintaining their shells, et cetera, et cetera, et cetera. By the way, the Lewis structure here for our carbonic acid is going to be something like this. And again, it's going to have that kind of C double bond OH functional group, and it happens to have two of them, one on each side. Okay, if we go again to our Wikipedia page here for carbonic acid, we can scroll down, and I hope we'll be able to find its pKa values. Oh, you know what? I don't think it has a pKa because it's not really going to be in a true equilibrium. It's not going to list it. Conjugate base, bicarbonate, carbonate. Yeah, it's not going to list it. It's about 6. Actually, you know what? Let me just see here really quick if I can Google a different source for it. Yeah, I'll do that later. I'll correct it in the comments. I'm going to guess it's about 6, and the reason I'm going to say that is that's about where our strips are. And so what happens with water as soon as you distill it, and by the way, in the chemistry lab, we aim for 18 ohm water, which is reverse osmosis purified. And the reason that we use ohms is a measure of electrical resistance. And the more resistance, the fewer ions that are in the water. And you can use that then. This is as high as water ever goes in terms of its resistance, and that is, quote, pure water. And so, you know, if you go to any really good source and buy even the most expensive distilled purified reverse osmosis water, and you measure its pH after a few minutes, it's going to come in at 6, because CO2 in the atmosphere is going to make carbonic acid, and the little bit of carbonic acid that's in there is enough to lower the pKa of that water to about 6. So there you go. So that explains our water conundrum. All right, so, you know, I'm hoping this clears up some confusion, and the reason I say that it is because I think the confusion is pretty severe in the field, and I say that not only because of things like how weak is our weak acid and hydrogen peroxide. Hopefully I've convinced you that while it is technically a weak acid, it's not going to wreck your comic book, because your comic book is already several orders of magnitude more acidic than it. And if we go look at our math, again, in the acidity range of that comic book, it is a literal fraction, an incredibly small fraction, that is actually contributing to the acidity. It's laughably small, and that would be true if it was 100%. This stuff is only 3%, and so, you know, it's even going to be less than that by about 97% less. And so there we go. Now, one thing I want to point out about the confusion being incredibly widespread is this is my brand spanking new official CGC guide to grading comic books. And, you know, if I go look this up, there's a section here on deacidification. And one thing that kind of irks the chemist to begin with here is they use the wrong symbol for pH, so it should be lowercase p, not capital H, but whatever, that's semantics. I won't go through and type check everything. But they have a paragraph here that they say, for comic books, water bath containing magnesium oxide or similar compound containing magnesium will deacidify. So magnesium oxide is MgO, and again, we can use our grand friend here, Wikipedia, and go look up magnesium oxide, also being called magnesia, which is pretty you know, standard, nothing too crazy about that. But what I want to draw your attention to is that when magnesium oxide gets wet, let's just say when you make a solution of it as recommended in the book, it actually makes magnesium hydroxide. And if we go look at magnesium hydroxide, we can get not only its solubility constant, but also recognize that it's part of antacids, milk of magnesia, etc., etc. And if we Google search the hydroxide, we can find out that that's actually the basic part of magnesium oxide. So what happens when you use magnesium oxide is you are generating magnesium hydroxide, and then the hydroxide is the base. And so while this book tells you that you might want to use other salts of magnesium, I assure you, you do not want to use other salts of magnesium, because it's not the magnesium part that's being basic, it's the oxide part. The oxide gets converted to hydroxide, and the hydroxide is the basic part. And you can just search that on your own, not that challenging there. But furthermore, if you're really curious, search up magnesium Lewis acids, and you can find all things reported to this that magnesium 2 is actually a Lewis acid because they accept a pair of electrons. And so if you use a different magnesium salt like magnesium chloride, not only would you not be applying base to your comic books, but you would be adding a Lewis acid to your comic books, which would be incredibly bad idea. All right, so, you know, again, there's a lot of misinformation out there. There's a lot of confusion. I understand that not everybody is a trained chemist. Luckily for you, I am. And so I'm asking you to just, you know, rewatch this video, gain some more understanding. If you have questions, feel free to ask me. I'm here to help. I don't mean to be elitist or anything about it. I really genuinely want the community to have more of an appreciation, not only for, you know, the acidity of their comic books, but also the, you know, impact that some things can have on that paper. And we'll go over some more chemical reactions here a little bit later, but it's not coincidental to me that the comic book is coming in at pH 4.5, because if we go look at our organic acids, you know, acetic acid's coming in that range, citric acid's coming in that range. The second pK of citric acid is very conveniently right on top of acetic acid. And what we're measuring is the organic acids that are present in the paper as they decompose. And so that is not surprising to me at all. And what it means is that if we want to think about deacidifying paper, especially in comic books, we don't need to use hydroxide bases that would be present in the magnesium oxide, and we also don't need to be worried about hydrogen peroxide, which again, while technically a weak acid, is such a weak acid that it's not going to do anything until we get well below, well above pH 8, which we're nowhere near experimentally. Okay, please leave a like, subscribe, thumbs up, reach out with questions, leave some comments, shoot me an email, find me on Instagram, etc. I'm here to help you. Thanks and take care.